Welcome to another video in our statistics series. So today we'll be looking at hypothesis testing, and hypothesis testing is probably one of the most challenging topics for most students that I've seen in the last few years. Normally when I ask someone, in statistics, what's the most difficult thing that you've seen? Often I'll find the answer is they'll say hypothesis testing is a chapter that I found quite difficult. And from my own experience, when I finished my high school, hypothesis testing is one of those concepts which, if it's not explained to you very well by your teacher, it can be quite a difficult thing to grasp. But once you kind of understand the basics, it's not as bad as it seems. It's actually quite a simple kind of process to do. So, what I want to do today is whether you've got teachers who've made it quite difficult for you to learn, or you just want to understand hypothesis testing better, then I'll try and take you through all of the different types of hypothesis questions you can get, and also I'll show you the standard way to write your answers. So today what we'll be looking at is we'll try to understand exactly why do we need hypothesis testing. I think it's important to understand why you're learning this topic in the first place so you can kind of appreciate and understand why you need to use it and how you can use it. Then apart from that, we'll be looking at how are we using samples and how do we use this to learn about a population. So in our previous videos, you've seen a lot about how we can conduct samples, how we can find samples, and now we're going to be putting these samples to use to learn about the population. Apart from that, when it comes to hypothesis testing, you need to understand what are critical values. So we'll be taking out critical values, which is something that if you've seen this topic before, I know a lot of people have some difficulty looking at critical values. So apart from this, we'll be taking a look at two different types of tests. There will be one-tailed tests and two-tailed tests. And we'll take a look at a few exam questions for each. So once we finish this chapter, what I'd like you to understand is basically what are hypothesis tests? Why do we need them? What are critical values? What are one-tailed tests? What are two-tailed tests? And most importantly, once you've understood the theory and how to do each of these, I want to show you how you can write out a standard exam answer for each type of question, because hypothesis testing literally follows the same kind of steps. Doesn't matter if it's one-tailed or two-tailed, you do the same steps and the answer is always in the same format. And for the exam, this is quite important. So I just like to kind of emphasize that quite a lot. So yeah, now that we've kind of gone through the introduction, let's just take a look at what exactly is hypothesis testing. So first, let's try to actually understand what is a hypothesis in the first place. So normally a hypothesis is something that you'll say where you're trying to learn something about the population. So a hypothesis might be something like, I think that in my school, the most popular TV show is X, Y, or Z. So there might be a TV show and you might think, okay, this is the most popular one in my school. Or it might be something like, I think that this, in this batch of eggs that I've got from the supermarket, I think that they're not very good quality or something like that. Basically, it's just something I'm trying to say about a population. So it might be me saying something like, I think if I flip this coin, it's not a fair coin, something like that. So a hypothesis is basically you saying something about the population parameter. So when we have a hypothesis, it's basically us trying to say something about a population parameter, like this. So that's the first thing to understand. I want to know something about my population, and a hypothesis is just a statement that I make about this. Is something that I say, I think that this, or I think that that. So I think that the most popular TV show in my school is this. So that is a statement I have made about the population, which is my school. So if I made a hypothesis, so I've made a statement now, I can actually test this hypothesis first. And then how do I do this? Well, the way that we always do it is we have to use some kind of experiment to figure this out. Now, as we've seen before, we've said that we could just ask every single person in the school what their favorite TV show is, and based on that, we can come to a conclusion. Now, the whole point of statistics, like we discussed before, is often impractical to take this kind of solution. So often we need to take a sample from a population and understand something from this. So the idea about the hypothesis testing is that now that we've made a hypothesis, which is a statement about the population, we can now test this hypothesis by using an experiment of some kind. And to do this, we often need to take a sample from our population. So if I've got my school full of all the children there, maybe I'll say I can ask 5 people from every class across every year group. And there's lots of different ways that you can be fair in your sample, or different samples that might make more sense in different situations. So we've covered that before in the video about how do we take samples and what are the advantages and the disadvantages of each kind of sample. So basically, let's say we have now done the experiment, then what's going to end up happening is that we're going to get some sort of statistic from this kind of experiment that we've done. And this statistic is known as your test statistic. So let's just kind of summarize everything that we've said here. So let's say I'm sticking with the school examples. I've got my population here. My population are all the people in my school. Now, I can't ask every single person within this population. So what am I going to do? Well, instead I say, well, since I can't ask everyone, doesn't matter what sampling method we use, but let's just simplify it for now. And so we use some sampling method. And using the sampling method, we've conducted an experiment. So we did an experiment. And this experiment allowed us to get a sample of some kind. So now we have a sample. Now, by conducting the sample, what we want to find is some sort of test statistic. So in our population, there is some population parameter that we're trying to find. So there's a population parameter, which is something like, this is the most popular TV show. 60% of people in my school like this TV show. And what we're going to find from our sample is a sample parameter. So that's over here, a sample parameter. And what this would be used for is we're going to compare this with the population parameter, and then we're going to infer something. So that's kind of what hypothesis testing is about. So we have a hypothesis, which is just a statement about our population. So we've got a population here. Then obviously we can't ask everyone, so we take a sample. When we take a sample, we have to do it by some sort of experiment. And the result of the experiment will give us a sample parameter, which we're going to compare to the population parameter. And essentially, that's kind of what hypothesis testing is about. So when it comes to writing down stuff about hypothesis testing, the first technical stuff that we need to know is there's something known as the null hypothesis. So I'm sure you've heard of this a lot when you've done this topic. So what exactly is the null hypothesis? Well, we normally denote this as H0. That's what it's known as. And this is a hypothesis that we think is correct. So we think this one is correct, or we assume it to be correct. So this is a hypothesis that you think is correct at the beginning. So I might say something like, I think the most popular TV show in my school is, let's say, SpongeBob SquarePants or something like that. I don't know, let's say it's primary school. And then I'll say that I think that 60% of students in my primary school like this TV show. So my null hypothesis is what I assume is correct. And then we also have something known as the alternative hypothesis. So the alternative hypothesis. And this one is denoted H1. And this is the one that is going to be, this will tell you that basically something about our parameter if the assumption that we made in that null hypothesis is wrong. So basically what it means is that I thought my null hypothesis was correct, but if it turns out it's wrong, the alternative hypothesis will tell me that this is actually the case instead. So this is like if your assumption or if your null hypothesis is wrong, then this is the case. So what this means is I carry out my hypothesis test. So I've done that now. And I think that this one is correct. So I think that, okay, the null hypothesis is correct. Let's say I did all my experiments, found my sample parameter, found my population parameter, and then actually it turns out my null hypothesis is wrong. Well, if my null hypothesis is wrong, I need something else that I need to know is correct. Because I can say, okay, fine, this isn't the most popular TV show, or this isn't like 60% of people at my primary school don't like this, then if that's not the statement which is true, then what is the statement which is true? Well, that's given by the alternate hypothesis. So basically, a hypothesis test goes something like this. My null hypothesis is either going to be correct or it's not going to be correct. So if it's correct, great. This is the statement, this one here, that you know is to be right. If that's not the case, then you know this is a statement, which is the one which is a correct statement. And in hypothesis testing, you're basically trying to find out, is this the one that's correct, or is it this one which is correct? And we'll talk a little bit more about how you can find these in the coming sections. So before we do that, let's just kind of give you an example of how we can conduct a hypothesis, at the beginning of a hypothesis test, where basically how do we set the null hypothesis and how do we set the alternate hypothesis. So let's come up with some sort of situation here. Let's say I have a 6-sided dice. I have a 6-sided dice, or I should say die technically. So I have a 6-sided die, and what I think about this die over here is that maybe it's not actually a fair dice. Maybe I keep rolling it and I find out that I'm thinking I'm always rolling a 6 for some reason, so I think it's not a fair dice. and I say, okay, I want to basically test this theory for myself, so I want to do my experiment. And to do this, I'm going to toss my dice. Let's say I roll the dice about 100 times, and I'm going to record the different numbers I get. So how many ones, twos, and so on do I roll? And basically, I want to see what the result is. So this actually lets you come up with a hypothesis. So I've got a six-sided die. I think that the side 6 is biased. So let's say I think it comes up more than it should. It could be possible that it comes up less, but let's say I think it comes up more than it should. So, and I rolled it 100 times as well. I had 100 rolls. So from this situation, what you can say is, what is my test statistic? This is the first thing you need to realize. What is my test statistic? So my test statistic in this case, we're going to denote it as x. And what is x going to be? X is going to be the number of sixes rolled in 100 rolls. That's what x will tell me. Literally all x will tell me is how many sixes I rolled, basically. That's what it's going to tell me. And when I've done 100 of them. That's all the test statistic is. Now let's say, what should my null hypothesis be? Well, my null hypothesis is a thing that I assume is going to be true. So I'll say, let's assume that the dice is a fair dice. So if it's a fair dice, then my null hypothesis, which is H0, what it should be is it should be that the probability of my 6 coming up should be equal to 1/6. That's what should be the case with a normal dice. If I roll it, I should get a 6 of the time. Now, if I think that the dice I've got, that this actually biased, then in that case, what I'm trying to say is my alternate hypothesis. What I'm trying to say is actually, you know what, the probability isn't 1/6. I think it's not a fair dice. So therefore, the probability of rolling a 6 is actually going to be more than a 6. And so therefore, I've written my H1 as being P, being more than 1/6. So this is basically what's going to be your alternate hypothesis. Now, that's kind of a basic beginning to it. Don't worry too much about the technical details of this. Just kind of try to understand why is my null hypothesis as 1/6 and why is my alternate hypothesis as more than 1/6, because when we get to solve an actual question with all the test statistics and the numbers and stuff like that, it'll be a lot more obvious what these are. So basically what we need to understand is that basically you can see here that we said that our alternate hypothesis was probability is more than 6, and we said it could have been less than 6 if the question was different. There are cases where actually sometimes we're going to find that the alternate hypothesis will be the case where it's not equal to. So we're not saying it's more than a 6 or less than a 6, we're just saying it's not equal to a 6. So for this, sorry, what we need to do is basically kind of see how do we use this. So basically what we're trying to say is if your alternate hypothesis is in the case of H1 is more than something, so sorry, H1 is your probability P is more than something, or your H1 is the probability P is less than something. In these two cases, these two are considered one-tailed tests because they're more than or less than. In the case that your alternate hypothesis is P does not equal to some value, then in this case, it's a two-tailed test. And basically, we'll be covering what each of these are. But just so you know, these are the 3 different situations that you can get. So if your alternate hypothesis looks like this with a more than or less than sign, then it's one-tailed, and if it's not equal to, then it's a two-tailed test. And we'll help you figure out, how can you figure out, is it a one-tailed or is it two-tailed? We'll kind of cover how you can figure that out in the coming examples, but this is just so you kind of have a heads up. So one other thing you need to do is you need to know when you're carrying out the hypothesis test, you always assume that the null hypothesis which you have is going to be true. And basically then we're going to do an experiment, find the test statistic, and basically after all of that, we need to decide, how rigorous are we with our test. So basically we say something like, okay, I assume my null hypothesis is true. I start with that. I think that H0 is true. And then I'm going to do my experiment, and that's going to give me a test statistic. As so. And basically what I need to do is consider how likely is it that this test statistic will occur. And is this likelihood, you have to compare it to like a threshold, and this threshold is known as significance level. So the significance level. And this is basically saying how stringent am I, how likely am I to reject the null hypothesis. So, how strict am I being? Is that the 1% level? Is that the 5% level? Is that the 10% level? The level will always be given to you in the actual question itself. Normally you can expect 10%, 5%, or 1%. And often the the bigger the significance level, the more stringent you're trying to be. So, if I have a 10% significance level, then I'm being very, very, I might be more likely to reject my null hypothesis, where if it's 1, then I'm less likely to reject it, but more on that later. Basically, for now, just think of the significance level as how strict are you being when you're conducting a hypothesis test. Okay, so let's actually try to understand what are critical values and what are critical regions. So normally, just so you know, as a starting point, the critical region it's basically the part of a probability distribution. It's a part of it where if your test statistic is within that, then you reject the null hypothesis. And just to help make more sense of that, the critical region is basically saying that, let's say we have some distribution. Since we know in this chapter we're working purely with the binomial distribution, the binomial distribution often looks something like this. And what often happens is that your test statistic can fall in different parts of this. So my test statistic could be here, it could be over here, it could be here, it could be anywhere. It depends on what you find it to be. And basically what we want to say is, if there's a region of this graph within which that test statistic falls, then anything in that region means we reject the null hypothesis. So let's say we found the region to be somewhere here. So let's say the critical region, we found that to be over here. Then let's say I found my test statistic. And my test statistic fell over here. Now, if my test statistic falls here, then I will accept H0. But if my test statistic falls anywhere within this red area, then I'm going to basically reject my null hypothesis. So these are the two different outcomes you can have. And the critical region is basically this whole shaded red area. So all of this part here, this is critical region, because that is a part where if my test statistic falls within that, then I reject the null hypothesis. And anything that falls within this green area, this is all fine. So the critical region is basically that. And the critical value is actually the first value of my critical region. So in this case, my critical value would be this one here. That's critical value. And it's useful to know because you know that if you fall on, let's say you fell on the right side of that critical value, you reject H0. Whereas if you fell on this side of the critical value, then you were to accept H0. So that's kind of the idea of what the critical region is. So yeah, basically that's the gist of the critical region. So I think it might be a good idea to kind of get a better understanding of it. And don't worry if it seems quite difficult at the moment, because when it actually comes to the questions themselves, we're going to be using a lot of these concepts and it will make a lot more sense when we actually do an example. But for now, I just want you to follow these kind of things separately. So I'll give an easier example to understand the critical region, how it kind of comes about. So let's say my test statistic was modeled binomially with n being 10 and p being some value. My significance level is 5%. And let's say my H0 is p equals 0.4. And my alternate hypothesis H1 is p is less than 0.4. But I think for this example, actually what I wanted this to be was I wanted p to be more than 0.4. Okay, so let's say that this is our situation. So what this means is that we assume, for the sake of the question, this is what you always do, that x is binomially distributed 10, and since the probability which was p here, we're going to assume that this probability is 0.4 from there. So we'll say p is 0.4. That's what we've got. Now, if you were to graph this binomial distribution over here, you would find it gave you something like this graph over here. Now, what we want to do is, we know that we're at the 5% level, and what we want to basically figure out is the same way we broke this diagram down here into the accept region and the reject region, we kind of also want to break down this diagram here into some kind of region where we accept it and some region where we reject it. So we need to figure that out. So how can we do that? So let's take a look at the probability that x is equal to 10. Now, if on this graph I know the probability x is 10, if I find that on the binomial tables, or you can use a calculator to figure it out, whatever you prefer, then you're going to find that this is equal to 0.0001, which is, that's fine. Let's carry on. Let's say what's probability x equals to 9. Probability x equals to 9, if you do the same thing in calculator, is 0.0016. And let's say the probability x is equal to 8. What is that probability going to be equal to? Well, that's 0.0106. So what do we find if we add up all these probabilities together? Well, if you add them all up, what this is going to give you, the probability that x is more than or equal to 8. So what happens if we add up all these numbers together as well? So if you add them all up, you get 0.0123. And 0.0123 is actually the same as 1.23%. Now, this value is less than our significance level of 5%. So because our 0.0123 or 1.23% is less than the significance level, then what we say for that is that any of these values would be rejected because all of them are less than 5%. So how does that look like on our graph? So over here, we found that its value for 10 was 0.0001. Its value for 9 was 0.0016. Its value for 8 was 0.0106. So when we put all of these together, what we found was it was less than 5%. And if it's less than 5%, then we're going to reject it. And why is it that we reject it on this side? Well, the key thing is that here we found that this is a more than sign. And because of more than sign, we know the reject region will be on the right-hand side of the graph. If this was a less than sign, then our reject region would have been on the left-hand side of the graph. But don't worry about that too much now because we're going to cover both left and right-hand sides later. For now, let's just concentrate on the fact that we're doing the more than sign, so that's on the right-hand side. So anyway, what have we done so far? We found the probability x is 10, x is 9, x is 8, and when we put that together, we got the probability x is more than or equal to 8, which gave us 1.23%. And 1.23% is less than 5%. And since this is the case, we so far know that any of these values, if you get it, you'd reject it. So what happens if we then move on to the probability that x is actually equal to 7? Well, if you try to figure out the probability that x is equal to 7, you get 0.0425. And then if I add up all of these values, so I add up the one for this, 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 and this, what I'm going to end up getting is I'm going to end up getting the probability of x being more than or equal to 7. And what this is equal to is going to be equal to, let's just add all of this up, 0. Well, actually, I don't need to worry about that, but let's do it anyway. 0.425 plus, I got 0.0123. So what does that equal to? 0.0548. Okay, now I've got that. And what does that equal to? That's 5.48%. Now, 5.48% is actually more than my significance level. And that means that this value here, which I just added on, 0.0425, this value took me over my threshold of 5%. Now, since it took me over my threshold of 5%, that means that if I get any value of x which is equal to 7, then I'm going to accept it. Same for x is 6, x is 5, x is 4, and so on. The only ones that I actually found that you're going to reject are the values 8, 9, and 10. Any of these values would give me a number which, when you added them all up, would be less than 5%. So any of these values would not work, so they would all be rejected. Any of these values here, as you can see, since when I added 7 is already more than 5%, then it doesn't matter which of these other values I take, all of these values will add up to something which is more than 5%. Now, since this adds up to more than 5%, then I can clearly say that this area here is the acceptance region, and this area here is the critical region over here. And what is my critical value? The critical value will be 8, since that's the first value in my critical region. So that's kind of the idea behind how that part works. So one other thing I'd like to help you out with is kind of try to understand, which side you reject, which side you accept, because this can get a little bit confusing for some people at some times if you've seen it. So I just want to kind of clarify that part for you. So normally what you're going to be given is you're always given a binomial distribution of some kind. a significance level of some kind, and the null hypothesis and the also null hypothesis. Now, using these parts of the question, the only thing you really need to worry about at this point is that is it a less than sign, is it a more than sign, or is it a not equals to sign? And like we said before, this kind of tells you about the fact whether it's a one-tailed or a two-tailed test. So now let's say it's a less than sign. When it's a less than sign, you know that your reject region is always going to be here on the left-hand side of the graph. So the same way we were trying to figure out before that, did stuff fall into the right-hand side? And we were trying to figure out those numbers. When you're doing questions for less than, you're actually going to be trying to figure out at which point does, let's say, this part exceed 5% here. And here you're trying to figure out which part does this exceed 5%. So if it's a less than sign, you always know your reject region is over here and your accept region is over here. If it's a more than sign that you've got to work with, then always your reject region is going to be on this side over here, and then your accept region is over here. So it's pretty simple to know. If it's less than, that's a reject region. More than, that's a reject region. And if you're doing a two-tailed test, where you have a not equals to sign, then what ends up happening is only one case. You have either this side or this side, you have two reject regions, and anything which falls in the middle is your accept region. And this will make a lot more sense when we do questions, but keeping this kind of thing in mind, it'll be quite useful to draw diagrams. And when we actually do a proper one-tailed test and a two-tailed test, I'll try and show you how you can kind of use these diagrams to help you, because they're not always taught in schools, or they're not really explained how you can use them. So I just wanted to kind of introduce that here so that when we do some questions, you're a little bit familiar with it to try. And like I said before, don't worry if all of this seems a little bit overwhelming or a bit difficult, because when we use all of this together in one question and give you a model kind of solution, it should be a lot more clear on how to use it. So for now, what we're going to do is we are going to go back. So what I also wanted to show you is how can you actually use the binomial tables to actually figure out what the critical region actually was, because you don't always want to keep adding up all the numbers like p is equal to, or x is equal to 10, x is equal to 9, x is equal to 8. That can take quite a while, and that's actually not how you do it when you're doing this in real life. That was just the theory. So what is a slightly easier method that we could use? So let's do the same question we did before. We had the fact that we had a binomial distribution of 10 and 0.4, and we want to figure out what is the critical region if you're given that kind of binomial kind of thing. So first thing you need to do is, since we can see n is 10, we need to look at the binomial tables where we have n is 10. And since we're dealing with the probability of 0.4, the only area or only column we care about would be this one over here. So that's what we've got now. So we know that our significance level that we were working with before, the sig level, that was 5%. So we know that. And we also knew that the also hypothesis we're working with, we had a more than sign in that. So since we had the more than sign, we know that we'll be working in this area of the binomial tables. If we had a less than sign, we'd actually be working in this area of it to see when it exceeded 5%. So at which point here does it exceed 5%? So here we can see there's no real cause for any concern, it's just a 1. Here, this still hasn't exceeded 5% because this is 0.998. Here we haven't exceeded 5% either because that's 0.988. But this number here is where we first, oops, that kind of disappears. But this number here, which is 0.945, is where we first exceed that 5% value. So now that we know this, how can we actually use that to figure out what the critical region is? So the way you do this normally is, the first thing you want to do is keep going through the numbers until you find the first one, which has exceeded 5%. So we clarified that the first 3 down here haven't exceeded 5%, and this one over here has. So I would like to kind of show you like the boundary at which point it flips. So I'm going to take I'm going to take this one here, which is 0.945, and I'm also going to show you how to calculate something for 0.988. So this value of 0.988, let's actually figure out, when we're looking at this one here, where exactly does this number, what value of a does this fall for? That's this one here, and this one over here is this one here. So I kind of want to talk about these two numbers over here. So what does the binomial table actually tell us? Well, the thing is, the number in the binomial tables are actually telling you the probability that x is less than or equal to a value of a, and a is basically given over here. So since I said that 7 here, then you could put that 7 here and get the probability that x is less than 7 is equal to 0.988. So that's kind of how this table is working. So this is what the table is telling you, the probability that x is less than or equal to a. So I'll put that up here. So how can we use that? So let's take a look first at this second highlighted line. So this tells us the probability that x is less than or equal to 7, and that means the probability of that is equal to 0.988. So we want to figure out a probability, because it's a more than sign, where the probability of x being more than a value of a is basically going to be less than 0.05. So that's where anything which is the case over there will tell us a critical region. That is basically what the critical region is. So to figure out this, you'll notice the difference is that here we have a more than sign, here we have a less than sign. So we need to kind of use the probability rules to flip that. So this is the same as doing 1 minus the probability of x minus 7. What will that give us? That will give us a probability that x is more than or equal to 8. And if we do that, we get 1 minus 0.988, which is equal to 0.0132. And as you can see, this value here is less than 0.05. So this part here is within the critical region. Now, if we did that for this one, or this one, we'd find that's the case for all of them. I want to show you what happens if you did it for the second one. So the first one, so if you did it for this line here, what actually happens? The probability that x is less than or equal to 6 is equal to 0.945. So 1 minus the probability of that will give you the probability of x being more than or equal to 7, which is equal to 1 minus 0.945, which is equal to 0.54. Let's take a look at that. 5, actually 0.55, my bad. So, my mental maths just kind of went out the window there, but this one here should be 0.055. And as you can see, this is equal to a probability which is more than 0.05. So this is the case where this is the acceptance region, this is okay. Whereas this one here, it was less than 0.05. So therefore, it's not actually going to be accepted and it's in the reject region. So based on this, we can say anything which is more than 7, this is okay. So where was the first time it was not okay? Well, it was not okay over here, which was p is, or probability of x being more than or equal to 8. So that means anything which is 8, 9, or 10, 8, 9, well, we don't have 10 here, but 9, 10, those values would not be accepted, whereas everything else would be accepted. So the key in this one here, this is just more for people who want like a deeper understanding of how it works, is essentially we wanted to find where is the value where it flipped. We found the value where it flipped was this one here between these two. So we know that based on that, the probability of this one here, of p being x less than or equal to 6, is equal to this value here. So when we flipped it, because it's more than sign, we found out, okay, this value works, so this is fine. So every other value which is here, when we did it, we found that didn't work. So that one there isn't fine. And basically what this tells us is, this tells us the critical region is anything which is probability x is more than or equal to 8. Don't worry, that was quite difficult and hard to kind of understand, but if you kind of follow it, it should hopefully make a bit of sense. But the key reason we're kind of trying to explain this is we want to learn of something known as the actual significance level. And the actual significance level, by its definition, is a probability that you'll incorrectly reject the null hypothesis. So what is the chance that you incorrectly reject the null hypothesis? That's the actual significance level. And how do we actually find that? Well, finding that is pretty easy. All you need to do is go to critical value. That's critical value there. And in this case, it's just going to be whatever number we got when we used the calculation for it, which is 0.0132. So this one here is the actual significance level. So you'll be working with 1%, 5%, 10% that give you the significance level. And if you want to find the exact significance level for a distribution, which is this one here, when you find out the first value, or the last value, the first value which did not work, when you find out whatever this number gives you, that's the actual significance level. So in this case, this tells us it's 1.32%. So that's kind of how to go through something like that. And yeah, I know this can seem quite difficult, but a lot of the time, once you start doing one-tail, two-tail test, you'll kind of start getting used to how to kind of make this kind of thing work. And what I'll try and do is I'll give you examples of a less than, a more than, and a two-tail test to make more sense of this. So let's take a look at that now. Also, I'd like to point out the value I'd used here. If some of you followed, that might not seem correct. That's because the value I'd used for this in my notes was actually 0.9877. So that's the value I'd used. And that's the value that basically got me to that number there after all the roundings. So don't worry, this is just because of that kind of reason. If I actually did this normally, this shouldn't have been that. It should have been 0.012, but it's the same idea. So that's all okay. But yeah, what I want to do now is kind of put everything into context and now start looking at a few exam examples. So some questions that you'll get in your exams and how you can solve them. So how can we use everything that we've learned? Don't worry if it's difficult. What I'll do now is actually get on to the example where I'll go step by step as to how you solve it, and you can try and follow this for some of the questions you have in your book and see if it makes sense. So I'm going over to the next part over here. We can see that we have a question where we have a binomial distribution where it's 6 in P. Our null hypothesis is 0.35, and our alternate hypothesis is more than 0.35, and our significance level is 5%. Now, since we have a alternate hypothesis of more than 0.35, that means the diagram in our head should be something like this one over here that we looked at before. We know there's some value where this is a region where we're going to reject, and this is a region on this side where we accept. So let me just use some colors for that one. This side here is a reject region, and this side here is the accept region. So that's the first thing that we do. We look at the question, see a more than sign, and we immediately draw this to kind of figure out what we need to do. And we also know the significance level that we have is 5%. Okay, great. So how are we going to start this question? Well, since we know that this question is given this way, we can write x is binomially distributed like this, 6. And we take this 0.35 and we put it in here. So what does that do? That gives us 0.35. Okay, this is the first thing we write down. Now I want to know what part of the graph should I actually be looking at? Well, I'll find the part where it's n is equal to 6, and I only care about actually this section over here where I have these numbers over here in the 0.35 column. So these are the only numbers that I should be using. So how are we going to do the question from here? Well, I want to take a look at where is the first point where my numbers are more than 0.05. And what I mean by that is this one here, and this one here. You can see none of these numbers, if you do 1 minus them, you'll get numbers which are less than 0.05, which means that these are the ones which you'll reject. But this one here, when you do 1 minus 0.05, and so 1 minus this thing, you get a number which is more than 0.05. So it's easy enough for me to say that, but I wanted to kind of go extremely step by step in this, so I'll actually show you what I mean by that. So if I find the probability of x being less than or equal to 6, that is apparently equivalent to this one, equal to 1. So if I do 1 minus the probability that x is less than or equal to 6, that gives me the probability that x is more than or equal to 7, which is equal to 1 minus 1, which is 0, which makes sense because for n is 6, the table shouldn't actually have gone that far. So then let's take a look at the probability that x is less than or equal to 5. That is equal to 0.998. So 1 minus the probability of x is less than or equal to 5 is the probability that x is more than or equal to 6, which is equal to 1 minus 0.998, which is equal to 0.002. And this here is less than 5%, so we know this is rejected. Then if I do probability x is less than or equal to 4, I get this is equal to 0.978, where, so if I do the same thing again, that's equal to 4, the probability that x is more than or equal to 5 is equal to 1 minus 0.978, which is equal to 0.022, which again is less than or equal to 5%. And you can kind of see the gist of what I'm trying to get at here. But basically, just by looking at all these numbers, you want to basically figure out which point where is it more than 0.55. And if you look at it, it should be fairly obvious that the number we're trying to look for is this one over here, where this is the first point at which it's more than 0.55. So based on that, how are we going to figure out what our critical region? So this is the first one where it works, and we want to figure out what the critical region is. So to do that, we need to find out the first value which didn't work. And what was that? The first value which actually didn't work was this one here. So what just happened? We tried to do 1 minus everything. We found that, okay, these values, that one is reject, that's reject, that's reject. And then we found, oh, at this point here, this is the one where we just suddenly accepted it. So what we want to do is go one back and take a look at what's the first point at which we rejected, which was this one here. And that's the only one we actually need to write any of this stuff out for. So this gives us a probability that x is less than or equal to 4, which is equal to 0.978. So this means if I do 1 minus the probability of x is less than or equal to 4, then that gives me the probability that x is more than or equal to 5. So let's do that. 1 minus the probability x is equal to 4, we found that's 0.78. So that's equal to 0.022. Now that we've seen that, this is the value at which it's less than 5%, and therefore anything which is over here, anything which is more than 5 is going to be rejected. So which values are more than or equal to 5? Well, only 5 and 6. Therefore, my critical region is going to be values where x is 5 or 6. So if x is 5 or 6, then we found that this is our critical region. So that's kind of how that works. So just to step over that again. They gave us the details in the question. We can therefore make this part here. The x is binomially distributed, 6 and 0.35, and the 0.35 we got from, well, not from this one over here, but we got that from over here, the null hypothesis. We assume that's true. Now, once we knew that's true, we took a look at this section of the graph, and we said, okay, if you do 1 minus that, it's not more than 0.05, this is fine, this is fine, this is fine, and then, oh wait, this one here, we've got a value which is more than 0.05 when we do the subtraction. So we said, okay, what is the point at which it flipped from being rejected to accepted? Well, it was between these 2 points. So once we found the points where it flipped, then we say, okay, we're only going to take the first one, which is rejected, which is this one here. Now, since we know this is the one that's rejected, we are going to take this value over here and then do this line here. How did we get the probability of x being less than 4 is this? This one came from here, and that 0.78 came from over here, 0.978. We put that there. Once we knew that, we know that if we do 1 minus that this thing is true. 1 minus the probability that x is less than or equal to 4 is the probability that x is more than or equal to 5. We then put that in here to get this, and then we solve that to find that. And once you found this one here, you can clearly see that that's obviously the first one you rejected, which you can tell. And therefore, the answer to critical region is the probability as x is more than or equal to 5, because it was that gave you this value over here. So it's 5 or 6 critical region. Notice that 4 is not in the critical region, even though it looks like it was accepted here. But the way you got your critical region was by doing this calculation, which actually only gave you 5 or 6 because of this over here. So that's kind of important to understand. And then someone might ask you, what is the actual significance level of this test? Well, the significance level of this test, the actual one, is just going to be that, which is going to be 2.2%. And that's all there is to it in the one-tailed test when it's the upper tail on that hand side. Now, what you can do if it was, let's say it was a less than, so let's actually get rid of all of the stuff that we've done here for a second, and let's actually change this around to being a less than sign. Then this graph no longer is the case, and what we actually end up having is we have something where, let's say, it's a less than sign, so we know that this side is now all going to be accepted, and this side is all rejected now. So what you end up doing here, so if I'll just erase all my highlighting and start all over again, then what we're going to find is that, well, it's 5%. So looking at these numbers here, where does it first cross 5%? Well, this is fine. This is less than 0.05. And actually, wait, sorry, my bad. This is not less than 0.05. So actually what we found is in this example, it's not probably the best example to use, but there's actually no value at which at the 5% significance level, which we're going to reject, because this number here is actually not even less than 0.05. So what this kind of tells us in this question is, in this case, if that was a diagram, pretty much everything would be accepted at the 5% significance level. So in this case, it would be completely okay. So yeah, don't worry about that too much for now. Let's take a look at some other examples. So yeah. Okay, so everything we've learned so far, all of the different examples you've seen, all of the different theories you've seen, I'd say all of that has probably built up to this kind of this part of the video, because here I'll basically show you how you lay out a one-tailed test, and if there have been parts which are confusing throughout the video, hopefully this part will help you bring it all together. So how do you actually solve an exam style question? Well, the first thing I just like to say is that to do these kinds of questions, there are a few things we have to follow. The first thing we have to do is we have to have a test statistic model. That's the first thing we need, a model for our test statistic. After that, we need a null hypothesis and an also null hypothesis. Then we need to basically figure out what the test statistic actually is. Once we know that, we need to look at the significance level. So we compare it. And once we've done that, we need to write up a conclusion. And this conclusion has to be based on the question that we've just tried to do. So when you're doing these kind of questions, keep this in mind. You have to have a model. So like x is binomially distributed in a certain way. You need to figure out alternate and null hypotheses. You need to figure out a test statistic. Then you have to compare this test statistic to your significance level. And then based on that, you either reject it or you don't. And based on that, you'll write a conclusion based on the original kind of question. Okay, so let's take a look at an example question here. So let's say I have a standard medicine, like the normal medicine I use to treat a disease. And that medicine, I have an old medicine, and the original medicine has a 0.4 chance of success. So there's a 40% chance that it works. And then someone comes along and says, you know what, I have this new medicine and I've tried it with 20 people. And from these 20 people, 11 were successes. And I'm saying that, okay, based on that, I think that my new drug or the new medicine that I've got is better than the old one that you had, because the old one worked with a 0.4% chance of success or 0.4 chance of success. And my new one, when I had 20 people, I had 11 successes, which I'll say is more than 40%. So I'm saying, I think that this is better. So then we're saying, okay, let's test this doctor's claim and see, is he correct? So we're going to set up a test at the 5% significance level. And that's what the question will be. So the way we do this is, the answer to this kind of question would be something like this. First, we have to have our test statistic, like we said. So we'll say x is the number of people for whom the medicine was successful. That's what X is. It's a number of people for whom the medicine was a success. And P is the probability of success. That's how I set it up. So it's X is the number of people for whom the medicine was a success, and P is the probability that I actually have a success. So X is binomially distributed, where I had 20 people, and with the probability of success of P for each of those 20 people. That's how you know it's binomial, either a success or it wasn't. Then I'll set up H0. So H0 is basically my probability is 0.4, which is what my success normally was. But because this guy is saying his drug is an improvement, well then what we're saying is the alternative hypothesis is probability is more than 0.4. So that's what's happening at the moment. Before, the guy said that my drug is better. So we're saying, okay, this is what I'm assuming is to be true, but you're saying that this is the truth if that's not the case. So how can I see which one is true? So now I need to actually figure out what is the test statistic going to be. So first thing that we know is that this is a one-tailed test. So let's just bring our table down here. Okay, so I've got n is 20 over here. And so what's our significance level? Our significance level was 5%. And what is our P? Our P is 40. So let's take a look at where is 40 on this graph. That would be over here. So the only column we're actually interested in would be this one here, for n is equal to 20. Okay, so first things first, just because of good practice, we'd say if we draw this graph, we know it's a more than, so we know basically our reject region is on this side. So we're looking for something over here from which to, on this side, from which to start doing our rejects. So as you can see, that's rejected, all of these values are all rejected because a 1 minus them would give you something which is less than 0.05. So all of those are rejected. So let's take a look at this one here. This one here is 0.998, which again would not work. But then let's take a look at the first one. So this would not work either, this would not work. Okay, here we found the boundary. So this part here, this is where our boundary is. Let's just draw that a bit more clearly. Okay, so why is this a boundary? Well, as you can see, if I did the one for 11, which is here, then I'd have 0.943, which 1 minus that would be okay. Whereas if I had 1 minus this one here, that would give me something which is less than 0.05, which would not work. So the value I want to take a look at is going to be this one over here. So when we do this one over here, let's write that down. So the way to work out would be the probability that x is less than or equal to 12 was 0.979. And why do we use this? Because it's the first value which doesn't work. We found the boundary was these two. This one worked, this one doesn't work because 1 minus that is less than 0.05. So we're going to do that here. So if you got that, then how do we find the greater than version? Well, 1 minus the probability of x being less than or equal to 12 is the same as the probability that x is more than or equal to 13. So 1 minus 0.979 is equal to 0.021, which indeed doesn't work. So therefore, our critical region is where x is more than or equal to 13. So that's anything which is more than or equal to 13. Now, the thing is, our test statistic is 11 because we found that when we did our test, our experiment, we had 20 people and we had 11 successes. So that is our test statistic, which is given to us. So we will compare that 11 to our critical region of 13. Now, if I just draw this graph that we had here again, so if I just, actually I'll just draw it from scratch, just draw a big version of it. So what I said that was, we found this thing here. We knew that anything on this side would be rejected. And then we actually found what this number here was. We found that this number was 13. So anything which is more than 13 is going to be rejected, and anything which is less than 13 will be accepted. And then we have a test statistic. So where does this test statistic fall? Well, the test statistic 11 would fall somewhere here. This would be 11 because that's 13. So that falls in the accept region. So what we found here is our test statistic does not give us enough evidence to reject, but instead we've accepted it. So what's important here is actually how you write the answer. So we say since 11 is not in the critical region, we will accept H0. But in terms of your exam answer, we never talk about the alternate hypothesis. So we never talk about rejecting or accepting the alternate. We only talk about the null hypothesis. So in this case, we'll say no evidence, or there is insufficient evidence to reject the null hypothesis. That's what we must say. So I'll just go back a bit. I'll write the answer. Insufficient evidence to reject the null hypothesis. And the claims of the doctor are wrong. And you'd say that the new drug is not actually better than the old drug. There's not enough evidence for him to say that the new drug is any better than the old one. So that's the important thing. The key thing I wanted to say to you is that you have to write there's insufficient evidence to reject the null hypothesis. If indeed we did find a test statistic was in this reject region, then we'd say there is sufficient evidence to reject the null hypothesis, and then we explain it in context that the doctor's new medicine is actually okay. It is better than the old one. But that's the kind of method we use. So you can see it's not too bad. This was all given to us. We used the significance level. We found, okay, which is the number at which it doesn't work first. It was this one here. Using that, we can find the critical region, which we found is x is more than 13. And we said, okay, this is 13. Our statistic is less than that, so we accept it. So everything is okay. So since we've done that, now let's actually take a look at a two-tailed example. Okay, so for our final example, we're going to take a look at how to write out the answer for a two-tailed test and the working that you'll need. So for this one, let's say that there's two restaurants. There's person A's restaurant and person B's restaurant. And what we found that was in person A's restaurant, 1/3 of people order vegetarian meals. And person B wants to basically figure out that are the number of people eating vegetarian meals in his one any different to that of those eating it in the other one. So he basically looked at 10 people and he found that only one person ordered a vegetarian meal, and he's trying to basically figure out, is there a connection that does the number of people eating veg in his restaurant is the same as the number of people eating vegetarian person A's restaurant. So there's two restaurants. This one has 1/3 of people eating veg, and this person wants to figure out if he also has 1/3 of people eating veg. And he's only been able to sample 10 people and found one person eats veg. So is that enough for him to decide that they have the same number of people eating vegetarian meals in both restaurants? So as usual, we have to say, what is x? So we'll say x is a number of people. X is the number of people eating veg at restaurant number B. That's what x is going to be. And P is the probability of ordering veg. So x is the number of people who eat veg at B, and P is the probability of people who order veg. So therefore my distributions, if I do it, is going to be x is going to be binomially distributed with, or actually let's not even start with that. Let's say first that, what's my null hypothesis? Well, my null hypothesis is that the probability of people ordering veg is 1/3. That's what I think. That is 1/3 of people who are indeed doing it. And my alternate hypothesis is that it's not 1/3. The question never said, is it more or less than 1/3? The question just basically states that is it 1/3 or is it not? So a trick in these questions is if it says, is it less than or more than, you know it's a one-tailed test. And if it says, is it not equal to, or is it this, then you know it's a two-tailed test. So here I'm saying that my null hypothesis, I think it was a third. But if it's not a third, then this is the case. So that's what it's going to be. My significance level is 5. So you write down sig level at 5%. And also we're saying that if H is true, then X is binomially distributed with 10 people at 1/3, because there are 10 people in a sample, and we're assuming H0 is true. So that's a third. So basically, what we need to do first is, let's bring this down again, this table, since we'll be using that quite a lot. So normally you won't have this kind of table in your exam booklet all the time. Like you have a booklet given at the end and it has like some binomial tables. Sometimes the values which you have to look at won't be in your binomial tables, so hopefully at school they'll teach you how to use a calculator to put in the values of n and put in the values of p, which actually gives you a calculator on your, the same table basically just on your calculator. So that's just something to keep in mind to figure out if you haven't already seen that already. Just you can ask someone at school, ask the teacher, look it up online, but it will be pretty useful. But anyways, what have we got so far? We have our null hypothesis, our alternate hypothesis, we have our significance level. So as we've always done, the first thing we need to do is draw the two-tailed graph. We know everything here is rejected and everything here is accepted. So what we need to figure out first is what are these two values in between which we accept. So for the lower tail, just make sure that you have this table actually first. I just want to make that point because you won't always get this table in your booklet that you have in the exam, because some values for p won't always be in the booklet and you have to learn how to do it on a calculator. Now for that I would ask your teacher how you do it, or just ask your friends, but basically just be comfortable coming up with the same table and calculator. The calculator method is basically the same thing that you find in your booklet. They both give you the same table. So in this case we had like p is a third, so you won't get that in your booklet, but in your calculator you should be able to have it. But anyways, taking a look at this, we want to figure out what's the lower tail. So based on what the lower tail is, what we want to see is which values do we reject and which ones do we accept. So first thing you have to remember is the significance levels. These are both 2.5% because we half it on a two-tailed test. So apart from that, let's take a look at our graph. We can see 0 has a value of 0.0173. Now that's less than 2.5%, so that one unfortunately is going to be rejected. Then over here, we can see that the value of 1 is 10.4%, and that's more than 2.5%. So that one is in the accept region. So all we can see here is that this is rejected and these are all okay, these values here. So we know that our lower critical value will be 0. That's a critical value there. Now there's nothing actually less than 0. So if you're bang on 0, then we're going to reject you. But obviously there's nothing less than 0 in this case, so we don't need to worry about that. So we know that, and now the only thing left is, what is the upper tail? Well, let's do the usual stuff we always did. So we have to do 1 minus each of these numbers and see at which point is that going to be more than 2.5%. So as you can see, this one would be rejected, 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 rejected. Oh, but this one for 5 would be accepted because it's 0.92 and we're trying to get the 2.5%. So as usual, we found the boundary, and then we look at the first one, which we would have rejected, which is this value for 6, where it's 0.9803. So we write the probability that x is less than or equal to 6 is equal to 0.903. So 1 minus the probability of x minus is less than or equal to 6 is the probability that x is more than or equal to 7. Therefore, 1 minus 0.9803 is equal to 0.0197, which is indeed less than 2.5%. So we know therefore the critical region is anything where x is more than 7, so any of these values here. So we can fill that in, 7. Now as we saw before, our test statistic is 1. Why is that? Because we did our experiment, only one person had veg, and 1 falls right here. And therefore there is not enough evidence for us to do a rejection, because you can see it falls in the accept region. So we'll say there again, there is insufficient evidence to reject the null hypothesis. Remember, we always talk about the null hypothesis, and we'll say something in context like there is not enough evidence to say that the proportion of people in A's restaurant is different to the proportion in B's restaurant. So always remember to add that on after that for the context part. And yeah, that's pretty much it. So normally in these two-tailed things, all you have to really do is figure out what this value is, figure out what this value is. So you see, okay, reject, reject, or so on. So here we said reject. This is fine, 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 and then these are not accepted. That's basically what we found. So we found that these are all the regions in which we reject. Where does that statistic fall? Falls in that one, so it's okay. And two-tailed is basically just kind of doing that. So try a few more questions, you should feel fairly comfortable. And it does take a while, but after you've done it a few times, it should help you. If there are any questions you don't understand, then please let me know what those are and I'll try and explain that to you best I can. And with enough practice, there's only 3 things you need to know: how to do a lower-tailed one-tailed test, an upper-tailed one-tailed test, and a two-tailed test. So once you've kind of got used to doing that, finding what the critical regions are, the critical values, and the test statistic, you'll actually realize it's not so bad. And just get used to laying out your questions like this. So just to recap it, say H0, say H1, say a significance level, write down the distribution, make sure you've said what X and P are, do your calculations, figure out the test statistic, figure out these values, see if it falls in there, and then you can just take it from there. Always remember to end with if there's either always going to be insufficient evidence or sufficient evidence, depending on whether you reject or accept, and then put the thing in context, and that should be good enough for this. If this is very difficult, let me know in the comments below if you'd like me to go through some more examples. So this video has covered a lot of the theory, so it might seem quite heavy, but in another video I can just do maybe 3 or 4 examples of a one-tailed and a two-tailed test just to give you a better idea, and I can write down exactly what I would in the exam as well in a slightly neater form, just if that helps some students, which I've seen before. But as ever, I hope this video was helpful, and just let me know in the comments below if you would like to see more of these videos. Until then, I'll see you in the next videos.